So many changes and shifts in networking technologies. Some of the changes are due to the demand of modern applications, right? And especially applications that are now hosted in many different environments, not only in a data center, but in many different cloud environments. So this complexity introduces risks, including network configuration errors and also network security challenges, right? Subsequently, networking functions like routing and optimization and security also have changed. And the next generation of hardware and software components in the enterprise need to support this rapid introduction and evolution of new technologies and solutions. So this network infrastructure, must keep pace with the business environment and support modern capabilities that will actually, at the end of the day, help drive simplification within the network. So these elements have helped with the creation of a concept called software-defined networking. And SDN, or software-defined networking, was actually originally created to decouple control from the forwarding functions in the networking equipment. And this is actually done to use software basically to centrally manage and program. This concept of programmability, right? And manage and program the hardware and virtual networking appliances to actually perform, network forwarding and routing and network functions. Now, traditional routing and switching, have actually addressed three different planes. You actually have the management plane, where you have configuration and monitoring, typically done via, a CLI or a GUI, and each vendor actually has their own proprietary way to configure the devices. And then you had control plane, and that's actually involved layer 2 and layer 3 protocols, and things like routing protocols like OSPF, RIP, BGP, and etc. Now you also have the data plane, and that's where, how data is actually forwarded inside of the hardware from interface to interface and from device to device. So in SDN, we introduced the notion of a centralized controller, and that SDN controller has actually a global view of the network, and it uses common management protocols to configure the network infrastructure devices, right? It also can use things like, RESTful APIs to provide configuration and streaming services to obtain telemetry from the network devices as well. Now, the SDN controller can also calculate the reachability information from many systems in the network and pushes a lot of set of flows inside switches and networking gear. Now, there are many different examples of open source and commercial implementations of SDN controllers. Now, an example is the Open vSwitch, or OVS, and it's a project using a database called the OVS database, or OVS-DB, for the management of the networking devices or network virtual devices as well. Now, the other one is OpenFlow, the OpenFlow protocol, and you're going to be learning a lot more about that later in the course. But I want to also give you somewhat of a preview of yet another example, but in this case, it's actually commercial and Cisco's implementation of an SDN controller, which is the Cisco Application Policy Infrastructure Controller, or Cisco APIC, right? And APIC is the main architectural component, or you can call it the brains, of the Cisco Application-Centric Infrastructure, or ACI solution. And those are actually great examples, and you're going to be learning a lot more about them later in the course. You're also going to be learning about the differences between northbound and southbound APIs in the SDN architecture, and also about other implementations like the Cisco DNA and the Cisco DNA Center. Implementations have northbound and southbound APIs. So what is actually a northbound and a southbound API? Basically, in an SDN architecture, a southbound API is used to communicate between the SDN controller and the switches or routers within the infrastructures. And these APIs can be open or proprietary. Cisco actually provides detailed information about all the APIs that are supported in different platforms in the DevNet website, or developer.cisco.com. I highly suggest for you to become familiar with this website. And not only that, but they actually provide a lot of different exercises and study material that you can actually use for free from Cisco. And later throughout the course, you're going to learn about using different APIs to perform different functions in networking devices as well. Now, Southbound APIs enable the SDN controller to dynamically make changes based on real-time demands and also based on scalability needs, right? Now, the OpenFlow and the Cisco UpFlex are examples that actually provide, or examples of implementations that provide Southbound API capabilities. Now, northbound APIs or SDN northbound APIs are typically RESTful APIs that are used to communicate between the SDN controller and the services and applications running over the network. So these northbound APIs can actually be used for the orchestration and the automation of the network components to align with the different needs of applications via SDN network programmability. So in short, northbound APIs actually are basically the link between the application and the SDN controller. In modern environments, applications actually can tell the networking devices, whether it's a physical, a system or a virtual network device or appliance, what are the types of resources that actually they need, and in turn, the SDN solution can actually provide the necessary resources to that application. Now, Cisco has a concept called the intent-based networking. And in many different occasions, you may see northbound APIs referred to as intent-based APIs. Cisco ACI provides the capability to automate settings and networking policies and configurations in a very, very flexible and scalable way. Now, in this example, I'm actually illustrating the concept of a centralized policy and configuration management in the Cisco ACI solution for your reference. Now, for this exam, you do not need to be an ACI, expert itself, right? So there's different CCNP and CCIE concentrations for data center, but I strongly suggest to at least become familiar with the concepts that I'm sharing here with you, and at least the overall functions and capabilities of the ACI solution. So ACI uses a leaf and spine topology. Each leaf switch is actually connected to every spine switch in the network with no interconnection between leaf switches or spine switches. Now the leaves have ports that are connected to traditional Ethernet devices, for example, servers, firewalls, even routers and so on. And then the leaf switches are actually typically deployed at the edge of the fabric. And these leaf switches provide the virtual extensible LAN or Vxlan tunnel functionality, right? And specifically the Vxlan tunnel endpoint or VTEP functionality as well. And you're going to learn more about Vxlan later in this course. Now, Vxlan, in short, is a network virtualization technology that leverages an encapsulation technique, very similar to VLANs, right, to enable and encapsulate layer 2 Ethernet frames within UDP packets, and typically it's actually done over UDP port 4789 by default, but it can be actually changed and configured depending on the implementation. Now, in Cisco ACI, the IP address that represents the leaf VTEP, right, or VTEP, is actually called the physical tunnel endpoint, or PTEP. Now, the leaf switches are responsible for routing or bridging tenant packets for applying network policies. Now, the spine nodes interconnect the actually leaf devices or the leaf switches, and they can also be used to establish connections from a Cisco ACI's pod, and that's a concept in ACI, a pod, to an IP network or to interconnect multiple ACI pods, right? And spines or spine switches actually will store all the endpoint to VTEP or VTEP mapping entries. Now, all leaf nodes connect to all spine nodes within a Cisco ACI pod. However, there's no direct connectivity allowed between the spine nodes or between the leaf nodes themselves. All workloads in ACI connect to leaf switches. Now, the leaf switches used in the ACI fabric are top-of-rack switches or TOR switches. The acronym TOR here is not the same as the onion router. If you're familiar with that, the solution used for anonymity and to access the deep web, that's not what I'm talking about here, right? Now, another thing to highlight is that the APIC or the controller, right, can be considered a policy and topology manager, right? So basically, APIC is the brain of ASIC or ACI rather, and APIC actually manages the distributed policy repository responsible for the definition and deployment of the policy-based configuration in the ACI infrastructure. Now, APIC also manages the topology and the inventory of all the devices within the ACI pod. Now, APIC also has a few additional functionalities, different functions, and here are the most common. First, it actually monitors the subsystem of the, ACI infrastructure. The APIC Observer is a function that actually monitors the health, the state, and the performance of the actual ACI pod. And then you also have the boot director, which is actually the function in charge of the booting process and the firmware updates of the spine switches, leaf switches, and the actual APIC components itself. Now, the appliance director is an APIC function that manages the function and control of the APIC appliance cluster. And then you also have the VMM, or the virtual machine manager, that is an agent between the policy repository and a hypervisor. For example, something like VMware vCenter and so on. Now, you also have the event manager, and if the event manager manages and stores all the events and faults initiated from the APIC and the ACI fabric nodes. Then lastly, you have the appliance element, which maintains the inventory and the state of the local APIC appliance. Now, for your reference, I'm actually including a link to the ACI Design Guide, which actually provides comprehensive information about the design, the deployment, and the configuration of the ACI solution. For this exam, you do not need to know, very details of the configuration of the ACI solution. Again, we actually have separate exams for that and certifications, but I strongly suggest to at least, read the document and become familiar with the, most important components, which actually already have covered here. But as a refresher, please use this as your reference. Cisco Digital Network Architecture, otherwise known as DNA, is also referred to as intent-based networking. Now, the DNA solution provides automation assurance services across campus networks, wide area networks, and also branch networks, so also including remote branch offices. Now, this solution is based on open and very extensible platforms and provides the policy, automation, and analytics capabilities that I'm actually showing here in the screen. So basically, at the heart of the DNA solution, DNAC, or the DNA Center, is basically the command and control element that actually provides that centralized management. Now, regarding the management, it can be done through dashboards, as you actually are seeing in the screen, and I'm doing a quick demo here of the DNA Center. But the more robust capability for DNA Center is actually the extensive APIs that it offers, right? So you can actually automate a lot and integrate many different other solutions like the Cisco Identity Service Engine and many others. Now in this screen, I'm actually just showing the ICE configure as an authentication, authorization, and accounting, or AAA server in the Cisco DNA Center and network settings screens. For the exam, you don't need to know all the different configurations for DNA Center. However, Cisco has a lot of sandboxes and active demos that you can take advantage of at DevNet and at the links that I'm actually sharing in the screen. Now let's go back to the Cisco DNA policies, right? So policies created in the DNA center can actually be group-based access control policies, IP-based access control policies, application access control policies, and also traffic copy policies. And basically here I'm actually showing the DNA Center policy dashboard. There you can actually see the number of virtual networks, group-based access control policies, the IP access control policies, and many others. Now, whenever you configure group-based access control policies, you need to integrate the Cisco ISE, so the Cisco Identity Service Engine, with the DNA Center. Now, in ISE, you can actually configure the work process setting as a single matrix. Now, I'm going a little bit beyond of what probably you will see in the text in the exam, because there are concentration exams for CCNP or the CCIE lab will absolutely concentrate on the configuration and troubleshooting of the deployment of DNA Center and the underlying network capabilities. Now, another thing that I want to highlight is that depending on the organization environment and access requirements, you can actually segregate your groups into different virtual networks to provide further segmentation. So whenever you integrate ISE with the DNA Center, the scalable groups that actually assist in ISE are propagated to the DNA Center configuration. So if a scalable group that you need does not assist, you can actually create it in Cisco ISE, and it will then be propagated to DNA Center. Now, DNA Center also has the concept of access control contracts, and a contract specifies a set of rules that allow or deny network traffic based on such traffic matching a particular protocol or a particular port. Now, as I mentioned to you, you can also configure IP-based access control policies, as I'm actually showing in here. You can also configure application policies in DNA Center, and these policies allow you to provide things like quality of service capabilities, but also application awareness capabilities as well. Now, in DNA Center, applications can be grouped into logical groups called application sets. These application sets can then be assigned a business relevance within a policy. You may also map applications to industry standards traffic classes that are defined in standards like the RFC 4594, for example. Another thing that you can configure in the Cisco DNA Center is the use of encapsulated remote switch port analyzer, or ER-SPAN. And basically that allows you so that the IP traffic flow between two entities is actually copied to a given destination for monitor or troubleshooting. So in order for you to actually configure ER-SPAN using DNA Center, you need to create a traffic control or traffic copy policy rather that defines the source and destination of the traffic flow that you want to copy. Now, the Cisco DNAC assurance solution also allows you to configure sensors to test the health of networking devices like wireless networks, right? A wireless network includes things like APs, WLAN configurations, wireless network services, and so on. Now, sensors can be either dedicated sensors or on-demand sensors. And a dedicated sensor is actually whenever you configure an access point or an IP, and then it's converted into a sensor, and it basically stays in sensor mode, and it's not basically used for serving wireless clients unless it actually manually is converted back to IP mode. So you have to keep that in consideration, because if you actually configure an IP as a dedicated sensor, that's the only thing that it will actually do. It will not serve any client, so no clients will terminate to that. So you have to think about that for in your deployment. Now, an on-demand sensor is actually whenever an AP is temporarily converted into a sensor to run tests, and after the tests are complete, the sensor actually goes back to AP mode. Now, as I mentioned before, one of the key benefits of the Cisco DNA Center is the comprehensive APIs that are available. They also call them intent APIs, right? But these intent APIs are northbound REST APIs that expose specific capabilities of the Cisco DNAC or Cisco DNA Center platform. And these APIs provide policy-based abstraction of business intent, so what you want to actually do, and then allows you to focus on an outcome to achieve, instead of struggling with a lot of the mechanisms that are part of the implementation, of course, you can actually automate, and perform an extensible architecture, right? And at the end of the day, it will allow you to be consistent, and consistency also, drives towards security. Vxlan and what are network overlays? Now, many organizations use this concept of an overlay network model. Basically, deploying an overlay network allows you to tunnel layer 2 packets with different encapsulations, right? And basically, you're doing this layer 2 tunneling over a layer 3 network. So this overlay network uses quote-unquote tunnels to carry traffic across the layer 3 fabric, and these solutions need to allow the underlay to separate network flows between different tenants or administrative domains. Now, the solution also needs to switch packets within the same layer 2 broadcast domain, and also route traffic between layer 3 broadcast domains and provide IP separations. And traditionally, this is actually done via things like virtual routing and forwarding, or VRFs. But nowadays, a lot of organizations actually are using Vxlan to provide this type of functionality. Now, there have been many multiple tunneling mechanisms, as I mentioned. Now, these are some of the most popular, historically. I just mentioned Vxlan, which stands for Virtual Extensible LAN. And you also have the network visualization with generic routing encapsulation, or NVGRE. You also have the stateless transport tunneling protocol, or STT, and the generic network visualization encapsulation, or GENEV, right? So GENEV. Now, the use of UDP in VXLANs basically enable routers and network infrastructure devices to apply hashing algorithms on the outer UDP header to basically load balance the network traffic. The network traffic that is actually writing the overlay network, it's actually load balanced over multiple links using equal cost load balancing, or equal cost multipath routing, ECMP. Now, this introduces a little bit better solution compared to the traditional network designs. In traditional network designs, access switches connect to the distribution switches, and this actually causes redundant links to block due to spanning tree. In this case, Vxlan uses an identifier, or a tag, that represents a logical segment that is called a Vxlan network identifier, or a VNID. Now, the logical segment is identified with a VNID, and it's basically a layer 2 broadcast domain that is tunneled over the VTEP tunnel, or the VTEP tunnel. Now, here I'm actually showing an example of an overlay network that provides a layer 2 tunneling capabilities. And in this other example, I'm showing an overlay network that provides layer 3 routing capabilities. Here's servers and different entities in the network were assigned subnets and VLANs, and they were pretty simple, but they try to provide some capabilities of segmentation. However, they also introduce a lot of complexities because application segmentation and policies were physically restricted to the boundaries of that VLAN, and specifically the boundaries of a data center or even in a campus environment. So in virtual environments, the problem became harder because nowadays applications can move between servers, it can move between data centers, and even between different cloud environments. So traditional segmentation based on VLANs will limit you to maintain the policies of which applications need to talk to each other, or who can access those applications, right? So this is ineffective because most traffic in data centers nowadays, or even in cloud environments, is east to west traffic. And a lot of traffic doesn't even leave the physical server and doesn't even hit a traditional firewall. But I mentioned, east to west traffic, and there's another concept called north to south traffic. So let me define that for you to actually get an idea, right? So east to west traffic is network traffic between servers, and it can be between virtual servers or physical servers or even containers. Now, north to south traffic is the network traffic flowing in and out of the data center. Now, many vendors actually have created solutions where policies are applied to applications and are independent from the location or the network that the application reside. For example, let's suppose that you have different applications running in separate VMs, and those applications also need to talk to a database, as I'm actually showing here. You can actually need to apply policies to restrict, different applications. Let's say application A, if they don't need to actually talk to application B, you actually can provide some type of policies to do this. And these policies should not be bound to a VLAN or to an IP subnet of the application. And especially nowadays that these VLANs and subnets are actually dynamically being assigned, right? So also network traffic should not make multiple trips back and forth between the applications and some centralized firewall to be able to actually enforce policy between them, and especially because of scalability. And then to put matters worse, containers make this a little bit harder because they move and change more often, right? So here I'm actually showing a high-level representation of an application running inside of a container, for example, a Docker container. And in this case, we have to have the ability to enforce network segmentation in those environments. And that's what we call in the industry microsegmentation. And microsegmentation is at the VM or at the VM level or at the container level, right? Basically between containers regardless of a VLAN or a subnet. Another thing is microsegmentation solutions need to be application aware. And that means that the segmentation process starts and ends with the application itself. So most microsegmentation environments apply a concept called the zero trust model. And this model dictates that users cannot talk to applications and applications cannot talk to other applications unless there's a defined set of policies that they actually permit them to do so.